Welcome back. So we'll continue the discussion on this aerodynamic forces and moments. So this is what we in the last session we have um, uh, written this flapping moment equation. Now, and these are all the non-dimensional term. I mean, they have been defined either by non-dimensionalizing based on the tangential component of the wind velocity or in terms of the angular velocity. So we have all the non-dimensional inflow, cross flow, total cross flow, Lock number, yaw rate term, wind velocity, everything. So now we look at the derivation of these components. So this aerodynamic forces and moments. So for the linear model, the component of the blade forces in tangential and normal directions are already calculated. So now what we'll account here, we'll account for number one, the flapping angle, and number two, um, zero drag. These are two things that we'll account for linearized system. Okay. Normal force, the normal force per unit length is Fn, that is L cos phi cos beta, and tangential force per unit length Ft sin phi. So these are the two different components. Now all the forces, so the various forces must be integrated or summed over the blade to give the shear force. Okay. Or multiplied by the distance first and then sum to give the moments. So, or multiplied by the distances first and then sum to give moments. So as before, we do simplification is made, and what we have, sine of phi is up by ut, cos of phi is 1, cos of beta is 1. So these are due to small angle approximation. Okay. Now flap-wise shear force at the root of the blade is the integral of the normal force per unit length of the blade. So what we have is beta 0 to r Fn dr 0 to r L cos phi cos beta dr 0 to 1 r d eta. Here eta is r by. So this is the flapwise shear force. Similarly, we have flapwise bending moment. The flapwise bending moment at the root of the blade. So is the integral of the normal force per unit length multiplied by the distance at which the force acts over the length of the what you have m beta 0 to r Fn r dr 0 to r cos phi cos beta r dr 0 to 1 squared eta beta. Now this flapping moment, so this can be expanded. So m beta is 0 to 1 r squared eta d 1 of PL alpha UP UT minus theta P UT square r square eta d. Now we can do other substitution as required. So go. Now if we put back the complete equation of motion, so this includes moments due to aerodynamic and yaw rate or gyroscopic effect, and then can have some algebraic manipulations. So it is beta double prime 1 plus epsilon g by omega square cos phi k beta by omega square ib in beta m beta omega square ib cos psi. Beta double prime is beta double dot pi omega square is the azimuthal second derivative of beta, and m beta is aerodynamic forcing moment. Now, if you see this equation now is expressed in terms of azimuthal derivative, which we will discuss further, because this will have some, once we write in terms of beta double prime, it would be easier um, to solve. So now from here, so this actually taking care of the yaw moment or moment due to yaw rate or moment due to aerodynamic forces. So this is what in terms of beta, second derivative of beta, we get the complete equation of motion. Okay. Now we'll further detail out this equation. So now if you recall the original flapping equation of free motion, when the aerodynamic and gyroscopic moments are included, that is written as beta double prime, beta double dot omega square 1 plus epsilon g cos psi k beta by ib into beta m beta by ib 2q omega cos psi. Now we divide by omega square, and what we get, beta double dot by omega square 1 plus epsilon g by omega square cos psi k beta by omega square I beta m beta by omega square ib 2q bar cos psi. So if you see this particular equation here, it is in time domain. Okay. The rotational speed is assumed to be constant. It is more interesting to express the equation as a function of angular or azimuthal position. So now we use chain rule. Beta dot is d beta by dt. We can have d beta by d psi by dt, which is omega d beta by d psi omega beta prime. Similarly, one can find out beta double dot equals to omega square beta double prime. So obviously you can see the dot stands for time derivative, and mm, that prime or single prime or double prime uh, stands for derivative with respect to azimuth. Now, once we rearrange this flapping equation of motion first, now we'll rearrange. So what we'll do, rearrange flapping equation of motion for solution. So now once we incorporate or substitute everything there, what we have is that beta double prime plus gamma by 8 1 minus 4 by 3 v prime cos I beta prime plus 1 plus epsilon g by omega square cos psi gamma v naught by 6 sin psi k beta omega square ib beta minus 2 q bar cos psi minus theta p by 4 gamma by 8. So gamma by 8 q bar sin psi minus cos gamma by 2 b 2 plus 2 theta by 3 k nu s q bar by 4. Okay, so this is v bar. Okay, now this can be written into slightly simpler form, like we can have beta double prime and plus gamma by 8, 1 minus 4 by 3 cos psi b naught bar plus q bar d bar beta prime k plus 2b cos psi gamma by 6 b naught sin psi beta gamma a by 2 gamma qr by 8 sin psi 2q bar gamma by 2 k3 plus q bar d bar k nu s u bar by 4 cos psi, where you have where k is flapping inertial natural frequency, so which includes rotation, offset, hinge spring. So this is given as 1 plus epsilon plus k beta by ib omega square. Okay. Now k is first axisymmetric flow term, which is theta p by 4. A3 second axisymmetric flow term, which is gamma minus 2 to theta p by 3. B is gravity term, which is g by 2 omega square, and d bar is normalized yaw moment term, normalized yaw moment, so which is d yaw by r. Okay, so what we have now, this equation actually includes all the forces. I mean, essentially includes all the restoring forces and all of the forcing terms. And now this can be used to find out the rotor behavior under a variety of wind and dynamic conditions. So this is complete, this equation that we have here. This is a complete flapping motion, includes all the, I mean, forced motion, but obviously once we make the all the aerodynamic forces and the yaw rate effect, then it becomes a free motion. So the free motion is a special special case of this particular generic equation which we have derived now for the force condition. So all these different terms like defined here, they are kind of, so they are all defined here, and this is an equation which includes all of the restoring forces and moments, and this now can determine the rotor behavior under a variety of wind conditions and dynamic conditions. As I have said, the free motion could be a special case of this equation if we make the right hand side zero, which is due to the aerodynamic force. I mean, effect all the force and moments due to aerodynamic force, linearized aerodynamic force, and force and moment due to your rate. So now once we have this generic equation, we can now look at different condition or different situation to find out the solution. Now again, the impact here is that, so what we just quickly go through, so this is where we derive the flapping equation for the free motion, and we can see right hand side there is no effect, and then we start deriving the forced equation which is incorporating the effect due to yaw and wind speed. And to do that, we have taken the linearized aerodynamic forces, so that we have derived, and for that we get these velocity components which will include all the effect of wind shears and things like that. This is the diagram that we started off, and then finally we take care of crosswind effect, wind shear effect, yaw motions, everything, vertical wind shears, all these we have included, and then we got this, and then the moment equation, that flapping moment we have, and then that also component wise derivation we carried, and finally we reach to this particular equation. So this includes all kinds of forces, moments, everything included, so that it allows us, again, this linearized systems or simplified equation model is very, very handy or useful for getting initial design data. Okay, we'll now look at the different solutions and all these things of this in the next session. Thank you.